We're going to start this video with a quick review about what zeros are. So hopefully you remember a little bit, but if you don't, here it is. Recall the zeros of a function f are the x values such that f of x equals 0. Right? These are just the y-intercepts. Okay, how do we make this function equal to 0? Y-intercept is when, x-intercept is when y equals 0. These are the x-intercepts. Okay, and we can solve these. We can solve this question by everyone's favorite method, capital F for fun. Can solve by factoring. Woohoo! Look at all these smiley, happy faces. This person is looking the other way because they're excited. All right, so let's start with some examples on that. If you need extra factoring resources, don't hesitate to reach out. Factoring is important here, and it will be important in your future math career as well. It's a good skill to have. Find the zeros of x to the 6th minus 3x to the 4th plus 2x squared. All right, when is this function f of x equals this? When is this function equal to 0? Well, this function is equal to 0, right? When, well, we can just write it like this. And we need to solve this equation. This is how we find the zeros. The zeros are when the function equals 0. So set the function equal to 0. Now, most of you, I guess I'm excluding myself. I have a lot of experience with this. Most of you probably don't have that much experience factoring with high degree polynomials, right? This is a 6th degree polynomial. The degree is 6. This is the leading term right here. But whenever possible, any factoring situation ever, if you can factor out something from everything, do that first. So notice each of these terms has an x squared that we can pull out. There's no numbers that we can pull out, but they all have an x squared. So let's factor that out. Pull out an x squared, and what's left? We took out 2 of those x's. There's 4 left on the first one. There's 2 left on the second one. And there's no x's left on the third one. We've made progress. We need to keep factoring. And again, you might say, oh, x to the 4th, Jason, I don't like x to the 4th. Well, that's okay too. This is a trinomial with leading coefficient 1. Even though this is x to the 4th, the fact that this middle one's an x squared and the last one's a constant means we can factor this pretty similarly to how we factor other trinomials with leading coefficient 1. The only way to get an x squared on the middle and an x to the 4th at the start is if this is an x squared and if this is an x squared. When in doubt, we can always check our answers by foiling it out. Hey. So then what do we have to look at? Different people do this different ways, but we need 2 numbers that multiply to positive 2 that add to negative 3. All right, we need 2 numbers that multiply to positive 2 that add to negative 3. And our answers are going to be negative 2 and negative 1. So negative 2, negative 1. Here we go. We're fully I can't even say it. I can't lie to you guys. We're not fully factored. It kind of looks like we are, but remember this thing is what's known as the difference of squares. Yeah, this is a lot of factoring review. Let's copy what we have down so far. All right, we have x squared, just because I'm getting to the next page. This is what we have. And remember that if I have a perfect square minus another perfect square, this is called the difference for subtraction, of squares. because each one of these things is squared. This is a minus b times a plus b. So 2 isn't a perfect square. We're not going to do anything with that. But this thing over here is. So x squared, just like before. X squared minus 2, just like before. But now this factors into a minus b times a plus b. So the red thing is the same thing as this red thing. And now it's fully factored. Why does factoring help us find zeros? It's because anytime you multiply by 0, your answer is 0. So if any one of these pieces is 0, we have a solution. Because we want to know when the whole thing is 0 and they're all getting multiplied together. So this is going to be true when the first thing equals 0, when the second thing equals 0, when the third thing equals 0, and when the fourth thing equals 0. There's going to be a lot of solutions here, a lot of zeros. So the first one, we can square root both sides. X is plus or minus the square root of 0, but plus or minus the square root of 0 is just 0. The second, add 2 to both sides. When x squared is equal to positive 2, take the square root, and whenever you square root both sides, you need that plus or minus. Don't forget me. The other ones are a little easier. Add 1 to both sides, subtract 1 to both sides. 0, plus or minus square root of 2. 1, negative 1, let's write it all together. The zeros of this function occur here, here, and here. We can combine positive 1 and negative 1 to just plus or minus 1. There we go. That problem took a little longer than I thought it was going to. Ha! It's a good problem, though. All right, I just want to do one more just for factoring review. F of t equals t cubed minus 5t squared minus t plus 5. If there are 4 terms, a lot of times we factor by grouping. Let's group the first 2 terms together. Let's group the last 2 terms together and factor each one of these pairs together. So out of the first pair, what can we factor out of this group? They don't share any numbers, but they do share 2 t's. Take out a t squared, we're left with a t minus 5. And the last ones don't share anything either. But remember, for factoring by grouping, we want to get this again. We want a t minus 5. So we don't quite have that, but we're very close. If we factor out a negative 1, then the negative t becomes a positive t, and the positive 5 becomes a negative 5, and then we get it. So now we pull out another greatest common factor. Right? This has a t minus 5, and this has a t minus 5. So we're factoring both of these out. It's the opposite of distributing. Right? We factor out a t minus 5. And when we factor out that t minus 5, what's left over? Well, we're only left with a t squared here. And we're only left with a minus 1 there. Right? And we could undo this step, right? Multiply t minus 5 times this, you'll get this. Multiply t minus 5 times this, you'll get this. All right, that's what's going on here. Last step is to do one more factoring step. Difference of squares again. Becomes t minus 1 times t plus 1. The zeros are when t is equal to 5 and plus or minus 1. All right, we're going to do one more definition and then an example problem to kind of talk about it. A little exploration. So another definition, if f of x, if our polynomial function has a factor that looks like x minus h to the p, then we say there's a 0 at x equals h. We already saw this in the last problem, right? Here's a factor. So there's a 0 at 5. Here's a factor. There's a 0 at 1. Here's a factor. There's a 0 at -1. And then specifically a factor, a 0 at x equals h of multiplicity p. That's our big definition here. All right. And then different things happen graphically. P does different things and it affects the x-intercept. Let's not use letters. Bullet point. If P equals 1, something's going to happen. P equals 2, something's going to happen. P equals 3, something's going to happen. If P is bigger than 3, something's going to happen. Let's explore, shall we? You don't have a choice. Actually, you do have a choice. You could just stop the video right now and say, Jason, I'm done with this. Jason, I didn't sign up for it. Well, you did probably sign up for this, but maybe you don't want it anymore. Let's come up with something. Let's look at, oh, it always does this to me. Don't do that to me. Let's look at, let's just look at a bunch of things with multiplicity 1. So notice, what happens if I change this first factor, x minus 1? That's going to be this. Let's do the x plus 2. Let's look at this 0 right here. This x plus 2. 0 at -2. What if I make the multiplicity into 2? The whole graph changes, but just look right here. Keep your eyes right here and see what changes. Multiplicity 2. Multiplicity 1. Multiplicity 2. Multiplicity 1. So how it crosses changes. Specifically, look at this. Look at this. This is exciting. Let's zoom in. Ooh, it kind of looks weird. We're zooming in a lot. What does this look like? Multiplicity 1. Well, it looks like a line. It looks like a line, kind of like y equals x. It's a steeper line, but it's kind of like a line, like x equals, like y equals x, kind of. And if we make this a 2, what does this look like? Whoa! It looks like a parabola. The multiplicity determines what things look like around that 0. So if multiplicity 1 is kind of like a line, multiplicity 2 is kind of like a parabola, what do you think multiplicity 3 is going to be? A cubic function, perhaps? Whoa! I'm sorry, I'm disturbing my cats, but it's kind of cool, right? So locally, the multiplicity, let's stay zoomed in for now. Again, all right, let's just go all for it. 4, well, that was 5. 4 is kind of like a flatter parabola. 5 is like a flatter cubic. 6 is an even flatter, etc. That's what we're going to generalize here. And again, when we zoom out, it's only like a cubic function locally, right? The multiplicity just says, how does the 0 kind of behave? Cubic function, if multiplicity 3, it's going to behave like a cubic function where it crosses the x-axis. Multiplicity 2, it's going to function like a parabola right there. Multiplicity 1, it's going to kind of cross like a line. Man, I haven't gotten this excited teaching this material in a while. Y'all are bringing out the best in me. Okay? All right, so my beard's getting a little long and it's starting to... Y'all need to hear that. So if p equals 1, it kind of crosses like a line. It crosses the x-axis kind of like a line. So if this is our x-axis, multiplicity 1 means the function kind of very locally crosses like this. P equals 2, it behaves like a parabola. It bounces. off like a parabola. And maybe it bounces off the top, maybe it bounces off the bottom, who knows? But it looks like this. Again, this is our 0. This is our 0, that's our x-intercept. P equals 3 crosses like x cubed. Again, kind of looks something like this maybe, or maybe it goes the opposite direction, it depends. And if it's bigger than 3, then depending on whether it's even or odd, it's just like a flatter version of p equals 2 or p equals 3. And it depends on whether even or odd. Yeah, maybe it looks like, maybe if it's even, maybe it kind of looks like this, like extra flat. Or maybe if it's odd, it looks like kind of this, like extra flat. This last case is, we're not going to worry too much about it. I just want you to know it, but I'm not going to give you points based on how flat your thing is. Okay. Let's do an example. Let's tie all this material together. Example 2. Identify the zeros and their multiplicity. Part A. F of x equals x squared times x minus 1 times x squared minus 4 cubed. Be very careful on this one. It has to be fully factored. If it's not fully factored, we can't really say much. So watch out. This is not fully factored. Oh no. So let's make it fully factored. Most of it's okay. X squared, nothing to do with that. X minus 1, nothing to do with that. But this last one, let's go off to the side real quick, right? X squared minus 4 cubed. All right, let's think about that as x squared minus 4 cubed, kind of like this. So that thing in the parentheses, let's factor that. That's x minus 2 times x plus 2. It's all getting cubed. So that's each thing cubed. And now it's fully factored and in the right form. Okay, so x minus 2 cubed times x plus 2 cubed. Now it's fully factored, so the zeros. This is not in the form x minus h, but it actually kind of is, right? X squared, that's x minus 0 squared. So the 0 is when x equals 0, right? X equals 0, x equals 1, x equals 2, and x equals negative 2. With multiplicity, well, this one has multiplicity 2, multiplicity 1, multiplicity 3, and multiplicity 3, respectively. Respectively just means that the way that we're ordering the zeros is the same we're ordering the multiplicities. So this goes with that, this goes with that, this goes with that, etc. Just makes it a little easier for us to answer in fewer words. And we should be able to see this graphically. If I graphed this function, we had x squared times x minus 1 times x squared minus 4 cubed. Again, let's zoom in on the y-axis. Let's look from like negative 0.5 to 0.5. All right, that didn't really make anything better. We could zoom in and we could see that hopefully it behaves the way we want it to behave. So this -2 has multiplicity 3. It behaves like a cubic function. 0, multiplicity 2, behaves like a parabola. 1, multiplicity 1, behaves like a line. 2, multiplicity 3, behaves like a cubic function around there. Great. So the next one would normally just be given to you as a graph, so don't look. Don't look at the function, that's cheating. I'm not going to stop you though. All right, and now you can look. You might say, Jason, where's the function? We have to change our scale again. Ah, there it is. Looking at this function, where are the zeros? The zeros are the x-intercepts. There's a 0 here, a 0 here, and a 0 here. So let's write that down. For part B, it's going to be the zeros are x equals -2, +1, and +4. And the multiplicities, notice that locally this behaves like a parabola. It bounces off. Multiplicity 2. Locally, this behaves kind of like a line, right? If you really zoomed in, it would almost look straight. Multiplicity 1. Here, behaves like a cubic function. Multiplicity 3, respectively. And that's our answer for B. Let's see if this makes sense. X equals 4, multiplicity 3. Hey, we said that. X equals 1, multiplicity 1. We said that too. X equals -2, multiplicity 2. We said that as well. Excellent. All right, and we'll just do one more because this video is not long enough. Let's, yeah, that's sarcasm. It's long, but more problems, more fun. Don't look at what I'm typing. It's a secret. All right, now you can look. So again, we have the intercepts at -2, 0, and +2. And we have the multiplicities. This one over here is real flat. Look how, see how it's way flatter than this one? That means it's going to be higher than 2 from the multiplicity. It's still even because it kind of like a parabola, but it's really flat. So it's 4 or maybe even 6. Just say multiplicity 4. If you say 6, I'd give you full credit. It's not super clear. 0 still has multiplicity 1. And 2 has multiplicity of 2. It's not as flat. That'd be your answer for this one. And yeah, it turns out that it is multiplicity 4. You can see that exponent of 4 on that 0. Let me know if you have any questions. Good luck. And I've got nothing else. Have a good one.